We will now discuss the gas laws. In order to study a gas, there is a little more complexity involved in it, because a gas can have three states. What are the three states? The state of a gas can be described by its pressure P, volume V, and its temperature T. That means if you want to make a study of how the pressure varies with temperature, you need to keep the volume a constant. If you want to study how the volume changes with temperature, you need to keep the pressure a constant. If you want to study how the pressure varies with volume, you need to keep the temperature a constant. That means there are three different studies on a gas depending on which of the three quantities you keep constant. So we will start by discussing Boyle's law. Again, let me remind you, in order to study the relation between pressure and volume of a fixed mass of gas, we have to keep the temperature a constant. And this study is given by Boyle's law. So what does Boyle's law deal with? Boyle's law gives you a relation between pressure and volume of a gas when the temperature is kept a constant. Now we will use this concept as we go on. Now when the temperature is kept a constant, the changes that take place when temperature remains a constant is called an isothermal change. Isothermal change. Isothermal. So Boyle's law actually describes a law to study the isothermal change. Study the variation of pressure with volume when temperature remains a constant. And such a relation is given by Boyle's law. What does it say? It said the pressure of a fixed mass of gas is inversely proportional to its volume when temperature remains a constant. And you can actually study it by using the arrangement that we have used as a constant volume thermometer. If you disregard this fixed point, and if you make markings on this bulb, you can then measure the volume of the gas, and the manometer can measure the pressure and make sure that the temperature of the gas inside is kept a constant. So keep the temperature a constant, measure the volume and pressure, and you can make a study. Well, how do you make a study? You draw a graph of pressure against volume or volume against pressure and see how the change takes place. Now this law can be written as, how do you write this law? The pressure of a fixed mass of gas is inversely proportional to its volume. P is proportional to 1 over V, or we say PV is a constant when the temperature T is a constant. Now this is how you can write this law. We can say P is proportional to 1 over V, which means P equal to a constant divided by V. This is what the law means. Pressure equal to a constant divided by V, or P times V will remain a constant. That means pressure and volume can change, but pressure multiplied by volume will remain the same so long as the temperature remains the same. That is what is given by Boyle's law. Now the variation of pressure with volume of a gas at constant temperature is called an isothermal change. A plot of pressure against volume therefore is called an isotherm. If you can now obtain a graph of pressure against volume, that curve will be called an isotherm. Now here I have the isotherms for a particular substance at 3 different temperatures. You can see for a particular temperature, as volume increases, P will decrease. Pressure is inversely proportional to volume. So this is the isotherm for that substance, for that gas at the temperature T1. And now if you increase the temperature to T2 and keep that temperature a constant while you study the pressure and volume, you get a different curve, a different isotherm. Alright, let's now talk about the pressure law. Pressure law deals with the variation of pressure with temperature when the volume remains a constant. A relation between pressure and temperature when the volume remains a constant is given by the pressure law. How do you study that relationship? Well, you can again study it using this apparatus that we are already familiar with. You can have a gas inside the bulb and you measure the pressure at various temperatures, keeping the volume a constant. Of course, that's easy to do that on this. And then you can make a plot of pressure against temperature. The pressure of a fixed mass of gas is directly proportional to its Kelvin temperature when the volume is a constant. This is the pressure law. And we can write it as P divided by T. Remember, the temperature is the Kelvin temperature. Pressure divided by the Kelvin temperature is a constant when the volume V is a constant. Now, a plot of pressure against temperature in Celsius. You see, we measure temperature in Celsius. Therefore, when we do the experiment, we can make a plot of pressure against temperature in Celsius, and this will be the graph you get. You see, the pressure against temperature will be a graph that will cut the pressure axis. And if you produce that graph backward, you can see that graph will cut the temperature axis at negative 273.15 degrees Celsius. What kind of temperature is this? This is the absolute zero. This is the 0 Kelvin. That means 0 Kelvin, by this situation, we can say 0 Kelvin is the temperature at which the gas will cease to have any pressure. The gas will not exert any pressure. Why? Because its molecules are at absolute zero energy. Okay, now since this is the 0 Kelvin, if you now shift this axis, the P axis over to 0 Kelvin, you can see you will have a graph starting at the origin. And that tells you that pressure is directly proportional to the Kelvin temperature. So a plot of pressure against temperature in Kelvin passes through the origin. You see, this is the 0 Kelvin. So if you move the pressure axis all the way to there, then 0 Kelvin will be the origin, and the graph now starts at the origin. And you know, when the graph passes through the origin, it represents y equal to mx. In other words, y is directly proportional to x. Here, pressure P is directly proportional to the Kelvin temperature at that time. And you can see pressure is directly proportional to the Kelvin temperature. And what does that mean? Pressure is directly proportional to the Kelvin. This relationship gives us pressure is directly proportional to the Kelvin temperature, and I can write it like this. pressure is directly proportional to Kelvin temperature, or pressure equal to a constant times Kelvin temperature. And if you divide both sides by T, I have P over the Kelvin temperature is a constant. And this is the representation of the pressure law. Pressure divided by the Kelvin temperature is a constant. Let's now talk about Charles' law. A relation between volume and temperature when the pressure remains a constant. Charles' law. It's a similar law like the earlier one, which is the pressure law. Now, what does the law say? The volume of a fixed mass of gas is directly proportional to its Kelvin temperature when the pressure is a constant. Now, Charles' law can be represented as, can you represent this law just like we did earlier? Volume is directly proportional to the Kelvin temperature when the pressure is a constant. It means V over the Kelvin temperature is a constant. Just like earlier we found P over the Kelvin temperature is a constant. Well, a plot of volume against temperature will be like this. Volume against temperature in Celsius. Now, in the same way, if you produce this graph backward, that graph will cut the temperature axis at negative 273.15 degrees Celsius. Now, that is the 0 Kelvin. That means if you now move the volume axis over to 0 Kelvin, the graph of volume against Kelvin temperature, you see that? Volume against Kelvin temperature will be a straight line through the origin like this. It means volume is directly proportional to the temperature, which gives rise to V divided by T is a constant. Let's now combine all these three laws into one, the ideal gas law. Well, what are the three laws? The first law is Boyle's law. What does Boyle's law say? Pressure multiplied by volume will remain a constant when the temperature is a constant. What does the pressure law say? Pressure divided by the Kelvin temperature remains a constant when the volume is a constant. What does Charles' law say? Volume divided by the Kelvin temperature will remain a constant when the pressure is a constant. So these are the three laws. PV equal to CT. We can combine all those three together and write it like this. PV equal to CT. Now look at that, those three laws one more time. We get PV equal to a constant when T is a constant. P over T is a constant when V is a constant. And V over T is a constant when P is a constant. Does it make sense, therefore, to combine all these things and say, therefore, PV divided by T, is that right? I can say PV divided by T will remain an absolute constant. This is the combination of all these three. And that gives me PV equal to a constant multiplied by T. PV equal to CT. That is a combination of all the three laws. And now, what does C stand for here? C is a constant, and what does its value depend on? It depends on the amount of gas that you have taken for your study. So C here is a constant which depends on, whose value depends on the amount of gas you have taken. And I'm going to write the C as C equal to K times N, where N is the total number of molecules of the gas, and K is a constant. N is the number of molecules of the gas, and K is a constant called Boltzmann constant. You see? So this constant C, I want you to pay special attention here. This constant C is Boltzmann constant multiplied by the number of molecules of the gas. That gives us PV equal to K times NT. K is Boltzmann constant. I will give you its value as we go on. N is the total number of molecules that you have taken in your sample for study. The value of K is determined as K equal to 1.381 times 10 to the negative 23 joules per Kelvin. That is the value of Boltzmann constant. Alright, so we have PV equal to K NT. Now, do you know what Avogadro's principle says? If you have done a little chemistry, you would know that. According to Avogadro's principle, 1 mole of any substance under the same conditions of temperature and pressure contains the same number of molecules. 1 mole, that's the unit of measure, a basic unit of measure in chemistry or in any substance. 1 mole of a substance under the same conditions of temperature and pressure will contain the same number of molecules. If I take 1 mole of hydrogen, it will have the same number of molecules as 1 mole of oxygen under the same conditions of temperature and pressure. That number is called the Avogadro's number. This number is called Avogadro's number and is represented by Na, Avogadro's number. What does Avogadro's number give you? The number of molecules in a mole of a given amount of substance. Now, therefore, and this has a value, Avogadro's number is 6.03 times 10 to the 23. Any 1 mole of any substance will contain 6.03 times 10 to the power of 23 molecules under the same conditions of temperature and pressure. When you vary the conditions of temperature and pressure, it will change. And therefore, is it possible to write this N? What does the N stands for? N stands for the total number of molecules in your sample. Now, therefore, that N can then be written as N equal to small n times Na, where small n is the number of moles of gas that you have taken for your study. So, if you have taken a certain amount of gas inside this container, the number of moles of gas multiplied by the number of molecules per mole. You see, Na is the number of molecules per mole. So, number of moles multiplied by the number of molecules per mole will give you the total number of molecules in your sample. So, we will now write N equal to, this N we are going to write as small n times Na, where small n is the number of moles of gas and Na is the number of molecules per mole. And that gives us PV equal to NKNAT. Alright, what are these quantities? N is the number of moles, K is the Boltzmann constant, Na is Avogadro's number, and T is the Kelvin temperature. Now, this quantity K times Na, K times Na has got a great significance. K times Na is a great constant. We normally write it as uppercase R, and is called the universal gas constant. So the universal gas constant R is Boltzmann constant K multiplied by Avogadro's number Na. The product of those two famous constants is called the universal gas constant. So we can now write that relation PV equal to nRT. That is a beautiful equation in chemistry, where N is the number of moles of gas, R is the universal gas constant, which is equal to K times Na. I will want you to recall this relationship many times in the next few lessons. So keep track of this. This is the statement of the ideal gas law. So what does the ideal gas law tell you? Pressure times volume equal to nRT. N is the number of moles, R is the universal gas constant, which is given by K times Na times T. And I'm going to give you a couple of values for R. The values of R will depend on the units in which pressure, volume and temperature are measured. Now in chemistry very often, pressure will be measured in atmospheres and volume will be measured in liters. But in physics very often we measure pressure in Pascal and volume in meter cube. So depending on these units, the value of R will change. Look at this. When pressure is measured in joules, when pressure is measured in Pascal, when pressure is measured in Pascal and the volume is measured in meter cube, the value of R will be 8.314 joules per mole per Kelvin. That is the value of R when pressure is measured in Pascal, that is Newton per meter squared, and volume is measured in cubic meter. Now, when pressure is measured in atmosphere and volume is measured in liters, as very many times chemists do, then the value of R will be this. R equal to 0.08206 liter atmosphere per mole Kelvin. Now, this actually tells you that the volume is measured in liters and the pressure is measured in atmosphere. You can see, if you use absolute units, liter times atmosphere, when you convert that to Pascal, it will become a joule. That's right. Okay, so we will use the value of R, either this or this, depending on the units of pressure and volume. Alright, again, keep track of these values. Let's do an example. A gas is kept at a constant pressure. If its temperature is changed from 50 degrees Celsius to 100 degrees Celsius, by what factor does the volume change? So here, a gas is kept at a constant pressure. Constant pressure. That means we are studying the volume with temperature. What is the law that gives you the relationship between volume and temperature? Well, first of all, our initial temperature is 50 degrees Celsius. And remember, these laws always uses the temperature in Kelvin. So convert the temperature to Kelvin. 50 degrees Celsius is 273.15. For the purpose of our calculation, we're going to drop that 0.15. We will take 273 plus 50, which is 323 Kelvin. So convert temperature in degrees Celsius to Kelvin by adding 273 to it. T2 is 373. 273 plus 100, 373. So, for a constant pressure, what is the law that we're going to use? V over T is a constant. What does this mean? V over T is a constant. If V1 is the volume when the temperature is T1 and V2 is the volume when the temperature is T2, then V over T is a constant means what? If V1 and T1 are the volume and temperature in state 1 and V2 and T2 are the corresponding quantities in state 2, then V divided by T is a constant means that V1 over T1 equal to V2 over T2. That's the meaning V over T is a constant. You can take the gas into any number of states. V over T is a constant means V1 over T1 equal to V2 over T2 equal to V3 over T3 and so on. Alright, so in this case, if V1 over T1 equal to V2 over T2, then V1 divided by V2 will be equal to T1 divided by T2. Well, we are given the values of T1 and T2, therefore we can find the value of V2 over V1. T2 is 373 and T1 is 323, and that is 1.15. V2 over V1 is 1.153 means V2 equal to 1.15 times V1. That's right. So we have answered this question. By what factor does the volume change? V2 over V1 equal to 1.15 means the final volume is 1.15 of the initial volume. Okay, another one. A 10-liter vessel contains gas at a temperature of 0 degrees Celsius and a pressure of 4 atmosphere. How many moles of gas are in the vessel? How many molecules are there? We are looking for the number of moles of gas in the vessel. Obviously, you need to go back to the ideal gas law. What do we know here? We know the volume is 10 liters at a temperature of 0 degrees Celsius. The temperature is 273 Kelvin. Pressure is 4 atmosphere. Now remember, we got the volume in liters, pressure in atmospheres, therefore the value of R will be R equal to 0.08206 liter atmosphere per mole per Kelvin. Always remember to use the right value of R depending on the units of volume and pressure. So we got the volume, temperature, pressure, and the value of R. We can now obtain the value of N. PV equal to nRT is the ideal gas law. We have all these values except N. Therefore, N equal to PV divided by RT. That will be 4 atmosphere times 10 liters over 0.08206 liter atmosphere per mole per Kelvin times 273 Kelvin. And look at the units now. You can see liter and liter, atmosphere and atmosphere will cancel. Per Kelvin and Kelvin will cancel. And per mole will go up. The unit, when you simplify it, will be mole. N equal to whatever number you get, that many moles. So that will be 1.79 moles is the number of moles of that gas in that container. Okay? How many molecules are there? If you know the number of moles, what do you do to find the number of molecules? multiply that with the Avogadro number, the number of molecules in a mole. So the number of molecules in 1 mole is the Avogadro number, 6.03 times 10 to the 3 molecules. Therefore, the total number of molecules will be the number of moles multiplied by the number of molecules per mole. That will be 1.79 times Na. That will be 1.79 times 6.03 times 10 to the 23. That is 1.08 times 10 to the 24 molecules. Okay, let's do another one. A room is 6 meter by 5 meter by 3 meter. That means you can find the volume in meter cube. If air pressure in the room is 1 atmosphere and the temperature is 300 Kelvin, find the number of moles of air in the room. You can do that the same way we did in the previous case. If the temperature now rises by 5 Kelvin and the pressure remains a constant, how many moles of air leave the room? Alright, let's first find A by writing down the given values. First of all, pressure is 1 atmosphere. Temperature is 300 Kelvin. R is 0.08206 liter atmosphere per mole per Kelvin. Volume of air is, the room is 6 meter times 5 meter. How do you find the volume of the air in a room? Length multiplied by width multiplied by height. So the volume of air in the room is 6 meter times 5 meter times 3 meter. That is 90 meter cube. There's a problem here. If you want to use pressure in atmosphere, then the volume must be in liters. If the volume is 90 meter cube, how many liters are there? In order to convert meter cube to liters, 1 meter cube contains 1,000 liters. So multiply this by 1,000. You get 9 times 10 to the 4 liters. Now once you have all these values, N equal to PV over RT. So put in all these values as before, and we get the number of moles is 3,656 moles. You got so many moles of air in the room at that temperature. Now what is happening? The temperature rises by 5 Kelvin. Now you know that in the room the volume is going to remain a constant. Is that right? Alright. Now in B, when the temperature rises by 5 Kelvin, the final temperature is 305 Kelvin. So the new number of moles of gas in the room now will be N equal to PV over RT. Now pressure remains the same. We are told that the pressure remains a constant and the volume also remains a constant. Is that right? When the temperature increases, will the room change its volume? No. The room is made to a fixed volume. So the volume remains a constant, which is this. So that will be pressure multiplied by volume, and this is R, and this is temperature. The only thing that changes is the temperature. Now, that gives me 3,596 moles are contained in the room now. What was the original value? The original value was 3,000, I don't remember. The number of moles of air leaving the room is, the original value was this, 3,656, minus, now what is remaining is 3,596. So 60 moles of air has left the room. Alright? Another example. A container with a volume of 6 liter holds 10 gram of liquid helium. As the container warms to room temperature of 20 degrees Celsius, what is the pressure exerted by the gas on its walls? Well, let's pick the given data. The volume of the container is 6 liters. And we have 10 gram of liquid helium. Well, mass is 10 gram. The temperature is 293 Kelvin, 20 degrees Celsius. 20 plus 273 is 293 Kelvin. R is 0.08206 liter atmosphere per mole Kelvin. As the container warms to room temperature, what is the pressure exerted by the gas on its wall? Since the molecular weight, do you know the molecular weight of helium? If you look at the periodic table, it gives you the atomic weight. The molecular weight of helium is 4. That means 1 mole of helium has a mass of 4 grams. Now, if you don't know that, now try and make a note of this. The molecular weight of a substance in grams is numerically equal to the weight of, well, the molecular weight of helium is 4 gram, means 1 mole of helium has a mass 4 gram. If the molecular weight of water is, 32, that means 1 mole of water has a mass of 32 gram. Alright? So the molecular weight of helium is 4, means the mass of 1 mole of helium is 4 gram. And we have 10 grams of helium. How many moles of helium do we have? Each mole of helium has a mass of 4 gram. Therefore, 10 gram of helium contains 10 divided by 4, which is 2.5 moles. So therefore, 10 gram of helium contains 2.5 moles. Okay, so N equal to 2.5 moles. Now we have PV equal to nRT. We got V, we've got N, we've got R, we've got T. We can find the pressure. What is the pressure exerted by the gas on its wall? Pressure equal to nRT divided by V, and use all the given values. That gives you 10.12 atmosphere. Why is the pressure measured in atmosphere? Because we use the value of K in liter atmosphere per mole per Kelvin. So the calculated pressure will be in atmospheres. But you must be able to do any such problems using the gas laws and the ideal gas law.